The National Electrical Code, or NEC, mandates specific disconnect switch requirements for microturbine installations, primarily focusing on safety and operational maintenance. Typically, 2 disconnect switches are required, one located outdoors and the other near the main electrical room. The outdoor disconnect switch, according to NEC sections 695.16 D and 695.17 A, is essential for emergency shutdown purposes. Its placement within sight of the microturbine allows for immediate disconnection in scenarios such as fires or other critical emergencies, ensuring a swift and safe response. This requirement underscores the code's emphasis on rapid intervention to mitigate potential hazards associated with microturbine operation. The main disconnect switch, governed by NEC section 695.16 C, serves a different but equally important role. It is primarily intended for maintenance and servicing activities. This switch facilitates the complete isolation of the microturbine from the electrical system, providing a safe working environment for maintenance personnel during repairs or routine checks. The NEC stipulates that this main disconnect switch should be situated in a location that is readily accessible to maintenance personnel, streamlining the servicing process and minimizing downtime. The necessity of both disconnect switches stems from their distinct functions in ensuring safety and facilitating maintenance. Eliminating either switch would create significant compromises. Omitting the outdoor disconnect switch would negate the ability to perform a safe and immediate emergency shutdown, increasing the risk of damage or injury during critical events. Conversely, removing the main disconnect switch would severely impede maintenance and servicing operations, making these tasks more challenging and potentially hazardous due to the inability to fully isolate the microturbine from the electrical supply. Given the owner's preference to avoid 2 separate disconnect switches, an alternative solution involves exploring the use of a remote-operated disconnect switch. This setup involves installing a switch within sight of the microturbine that is remotely linked to the main disconnect switch located in the electrical room. Such a configuration effectively provides the required disconnect capabilities at both locations without necessitating 2 individual switches. When considering a remote-operated disconnect switch, several technical aspects must be carefully evaluated to ensure compliance with the NEC and optimal system performance. Firstly, the remote-operated switch must meet all applicable NEC standards for disconnect switches, including those related to voltage and current ratings, interrupting capacity, and enclosure type. Secondly, the control system for the remote operation must be reliable and fail-safe, preventing unintended operation or failure to operate when needed. Thirdly, clear and permanent labeling is essential at both the remote switch location and the main disconnect switch, indicating the function and location of each switch. Fourthly, the wiring and communication system between the remote switch and the main disconnect switch must be robust and protected against environmental factors such as moisture, temperature variations, and physical damage. The selection of appropriate disconnect switches is crucial for the safe and efficient operation of a microturbine system. The NEC provides specific guidelines for the selection and installation of these switches, addressing factors such as voltage rating, current rating, interrupting capacity, and environmental protection. Voltage rating refers to the maximum voltage that the disconnect switch is designed to handle safely. The selected switch must have a voltage rating equal to or greater than the system voltage to prevent insulation breakdown and potential hazards. Current rating indicates the maximum continuous current that a disconnect switch can carry without exceeding its temperature limits. The switch must be rated for the full load current of the microturbine system with an additional safety margin to account for overloads or fault conditions. Interrupting capacity is the maximum fault current that the disconnect switch can safely interrupt without damage to itself or the surrounding equipment. The interrupting capacity must be sufficient to handle the available fault current at the installation location as determined by a short-circuit study. Environmental protection refers to the enclosure type of the disconnect switch, which must be suitable for the intended environment. Outdoor locations require switches with enclosures rated for weather resistance, while indoor locations may use switches with less stringent enclosure requirements. In addition to these electrical characteristics, the physical construction and operating mechanism of the disconnect switch are also important considerations. The switch should be constructed of durable materials that can withstand the rigors of regular use and environmental exposure. The operating mechanism should be smooth and reliable, ensuring consistent and positive operation. The switch should also be equipped with clear and visible markings indicating its on and off positions. Proper installation of disconnect switches is essential for ensuring their safe and effective operation. The NEC provides detailed requirements for the installation of disconnect switches, covering aspects such as mounting, wiring, grounding, and labeling. Mounting the disconnect switch involves securely fastening it to a stable surface, ensuring that it is readily accessible and protected from physical damage. Wiring the disconnect switch requires the use of appropriately sized conductors and proper termination techniques to ensure a reliable electrical connection. Grounding the disconnect switch involves connecting it to the grounding electrode system to provide a low impedance path for fault currents, minimizing the risk of electric shock. Labeling the disconnect switch requires the use of clear and permanent markings indicating its function, voltage rating, current rating, and interrupting capacity. Regular inspection and maintenance of disconnect switches are crucial for ensuring their continued safe and reliable operation. Inspections should be conducted periodically to check for signs of damage, wear, or corrosion. Maintenance activities may include cleaning, lubricating, and tightening connections as needed. Any damaged or malfunctioning disconnect switches should be replaced immediately to prevent potential hazards. In summary, the NEC mandates specific disconnect switch requirements for microturbine installations to ensure safety and facilitate maintenance. Typically, 2 disconnect switches are required, one located outdoors for emergency shutdown and the other near the main electrical room for maintenance and servicing. If the owner prefers to avoid 2 separate disconnect switches, a remote-operated disconnect switch can be considered, provided that it meets all applicable NEC standards and is properly installed and maintained. Careful selection, installation, and maintenance of disconnect switches are essential for the safe and efficient operation of microturbine systems. Now, let's delve deeper into the specifics of selecting the appropriate disconnect switches, focusing on voltage, amperage, and other critical factors. Selecting the right disconnect switch involves a meticulous evaluation of the microturbine's electrical characteristics and the surrounding environmental conditions. The first and foremost consideration is the voltage rating of the switch. It must equal or exceed the maximum voltage present in the microturbine's electrical circuit. For instance, if the microturbine operates at 480 volts, the disconnect switch must be rated for at least 480 volts, and preferably higher to provide a safety margin. This ensures that the switch's insulation can withstand the voltage without breaking down, preventing potential electrical arcing or short circuits. Next, the amperage rating of the disconnect switch is crucial. It needs to handle the continuous current drawn by the microturbine under full load conditions. To determine this, you must calculate the full load amps or FLA of the microturbine. This information is typically found on the microturbine's nameplate. Once you have the FLA, select a disconnect switch with an amperage rating that is at least 115% of the FLA. This provides a buffer to accommodate any temporary overloads or fluctuations in current. For example, if the microturbine's FLA is 50 amps, the disconnect switch should be rated for at least 57.5 amps. Another vital factor is the interrupting capacity, also known as the short circuit current rating, or SCCR. This refers to the maximum amount of fault current the disconnect switch can safely interrupt without sustaining damage or posing a safety hazard. The available fault current at the installation location must be determined through a short circuit study conducted by a qualified electrical engineer. The disconnect switch's SCCR must be equal to or greater than the calculated available fault current. Using a disconnect switch with an insufficient SCCR can lead to catastrophic failure during a fault, potentially resulting in equipment damage, fire, or injury. The environmental conditions at the installation location also play a significant role in selecting the appropriate disconnect switch. For outdoor installations, the switch must be housed in a weatherproof enclosure that protects it from rain, snow, ice, and other environmental elements. These enclosures are typically rated according to NEMA, or National Electrical Manufacturers Association, standards. For example, a NEMA 3R enclosure provides protection against rain, sleet, and snow, while a NEMA 4 enclosure offers protection against splashing water and hose-directed water. For indoor installations, the enclosure requirements may be less stringent, but the switch should still be protected from dust, moisture, and physical damage. The type of disconnect switch is also an important consideration. There are several types of disconnect switches available, each with its own advantages and disadvantages. Non-fused disconnect switches are the most common type and are suitable for general-purpose applications where overcurrent protection is provided separately. Fused disconnect switches incorporate fuses within the switch enclosure, providing both disconnect and overcurrent protection in a single device. This can simplify the installation and reduce the number of components required. Motor-rated disconnect switches are specifically designed for use with motor loads and are capable of interrupting the high inrush currents associated with motor starting. These switches typically have a higher amperage rating and a more robust construction than general-purpose disconnect switches. When selecting a disconnect switch, it is also important to consider the ease of operation and maintenance. The switch should be easy to operate with a clear and visible handle position indication. It should also be easy to inspect and maintain, with readily accessible terminals and components. The NEC provides specific requirements for the installation of disconnect switches, covering aspects such as mounting height, working clearances, and labeling. The disconnect switch must be mounted in a location that is readily accessible and not obstructed by other equipment or structures. The NEC requires specific working clearances around electrical equipment, including disconnect switches, to provide adequate space for personnel to safely operate and maintain the equipment. These clearances vary depending on the voltage of the equipment and the presence of exposed live parts. The disconnect switch must be clearly labeled to identify its function and the equipment it serves. The label should be permanent and easily readable. Regular inspection and maintenance of disconnect switches are essential for ensuring their continued safe and reliable operation. Inspection should be conducted periodically to check for signs of damage, wear, or corrosion. The switch should be operated to verify that it functions properly and that the contacts are clean and free from corrosion. Any loose connections should be tightened, and any damaged components should be replaced. Now, let's further explore the specific NEC sections that govern disconnect switch requirements for micro turbines, providing a more detailed understanding of the code's intent and application. NEC Section 695.16, titled Disconnecting Means, outlines the general requirements for disconnect switches for micro turbines. This section mandates that a disconnecting means be provided for all ungrounded conductors of the micro turbine system. The disconnecting means must be readily accessible and capable of disconnecting the micro turbine from all sources of power. This ensures that the micro turbine can be safely isolated for maintenance, repair, or emergency shutdown. NEC Section 695.16 C specifically addresses the disconnecting means for maintenance and servicing. This section requires that a disconnecting means be located within sight of the micro turbine or be capable of being locked in the open position. This ensures that maintenance personnel can safely work on the micro turbine without the risk of it being inadvertently energized. The disconnecting means must also be clearly labeled to indicate its function and the equipment it serves. This helps to prevent accidental operation of the wrong disconnecting means. NEC Section 695.16 D addresses the disconnecting means for emergency shutdown. This section requires that a disconnecting means be located at a readily accessible location outside the micro turbine room or enclosure. The disconnecting means must be clearly labeled as the emergency shutdown switch and must be capable of disconnecting the micro turbine from all sources of power. This provides a means for quickly and safely shutting down the micro turbine in the event of a fire, explosion, or other emergency. NEC Section 695.17, titled Overcurrent Protection, outlines the requirements for overcurrent protection for micro turbine systems. This section mandates that overcurrent protection be provided for all ungrounded conductors of the microturbine system. The overcurrent protection must be sized and installed in accordance with the NEC requirements for overcurrent protection devices. This ensures that the microturbine system is protected from overloads and short circuits which can cause damage to the equipment or create a fire hazard. The overcurrent protection devices must be readily accessible and capable of being reset or replaced without exposing personnel to live parts. This facilitates maintenance and troubleshooting of the overcurrent protection system. In addition to these specific NEC sections, other sections of the code may also be applicable to microturbine installations depending on the specific design and configuration of the system. These may include sections related to grounding, wiring methods, and equipment installation. It is important to consult with a qualified electrical engineer or inspector to ensure that the microturbine installation complies with all applicable NEC requirements. The NEC is a comprehensive and complex document, and its interpretation and application can be challenging. Consulting with a qualified professional can help to ensure that the microturbine installation is safe, reliable, and compliant with all applicable codes and standards. Let's discuss remote-operated disconnect switches in greater detail. Remote-operated disconnect switches offer a compelling solution for situations where it is desirable to have disconnect capabilities at multiple locations without the need for separate physical switches. These devices essentially consist of a standard disconnect switch that is controlled remotely via electrical or mechanical means. One of the primary advantages of remote-operated disconnect switches is their flexibility in terms of placement. The control switch can be located in a readily accessible location, such as near the microturbine, while the actual disconnect switch can be installed in a more convenient location, such as the main electrical room. This allows for both local and remote control of the disconnect function. There are several types of remote-operated disconnect switches available, each with its own unique features and operating principles. Electrically operated disconnect switches use an electric motor or solenoid to open and close the switch contacts. These switches are typically controlled by a remote push-button or selector switch. Mechanically operated disconnect switches use a cable or linkage system to transmit the operating force from the remote control to the switch mechanism. These switches are often used in applications where electrical power is not readily available or where a more robust and reliable control system is required. When selecting a remote-operated disconnect switch, it is important to consider the following factors. The voltage and amperage rating of the switch must be suitable for the microturbine system. The switch must have an appropriate interrupting capacity for the available fault current at the installation location. The control system must be reliable and fail-safe, ensuring that the switch operates correctly when needed. The switch must be installed in accordance with the manufacturer's instructions and all applicable codes and standards. Remote-operated disconnect switches can offer a cost-effective and convenient solution for meeting the disconnect requirements of the NEC. However, it is important to carefully evaluate the specific application and select a switch that is appropriate for the intended use. Consulting with a qualified electrical engineer or inspector can help to ensure that the remote-operated disconnect switch is properly selected, installed, and maintained. Now, let's review how these concepts apply to a real-world microturbine installation scenario. Imagine a microturbine is being installed in a remote location, such as a wastewater treatment plant or a cell tower site. The microturbine is located outdoors, and the main electrical room is located several hundred feet away. In this scenario, it would be impractical and costly to install two separate disconnect switches, one near the microturbine and one in the electrical room. A remote-operated disconnect switch could provide a more practical and cost-effective solution. The disconnect switch could be installed in the electrical room, and the remote control switch could be installed near the microturbine. This would allow personnel to safely disconnect the microturbine from either location. The remote control switch could be a simple push-button or selector switch, or it could be integrated into a more sophisticated control system. The control system could also provide remote monitoring of the microturbine's operating status, such as voltage, current, and power output. This would allow personnel to remotely diagnose and troubleshoot any problems with the microturbine. The remote-operated disconnect switch would need to be carefully selected and installed to ensure that it meets all applicable NEC requirements. The switch would need to have an appropriate voltage, amperage, and interrupting capacity for the microturbine system. The control system would need to be reliable and fail-safe, ensuring that the switch operates correctly when needed. The switch would need to be installed in accordance with the manufacturer's instructions and all applicable codes and standards. In addition to the remote-operated disconnect switch, the microturbine system would also need to be equipped with other safety features such as overcurrent protection devices and grounding electrodes. These safety features would help to protect the microturbine system from damage and prevent electrical hazards. The microturbine system would also need to be regularly inspected and maintained to ensure that it continues to operate safely and reliably. Inspections should be conducted periodically to check for signs of damage, wear, or corrosion. Maintenance activities may include cleaning, lubricating, and tightening connections as needed. Any damaged or malfunctioning components should be replaced immediately. By following these guidelines, it is possible to safely and reliably install and operate a microturbine system in a remote location. Remote-operated disconnect switches can provide a cost-effective and convenient solution for meeting the disconnect requirements of the NEC. However, it is important to carefully evaluate the specific application and select a switch that is appropriate for the intended use. Consulting with a qualified electrical engineer or inspector can help to ensure that the remote-operated disconnect switch is properly selected, installed, and maintained.